This lecture is about principal component analysis. This is a neat way to use the singular value decomposition to get insight into numerical data. The key purpose of principal component analysis, or PCA, is to identify the directions of maximum variance in data. Variance has a technical definition, but for now let's just think of it as the amount of spread in the data. So if I look at this data, a collection of points in R2, I can see that it's pretty well spread out in this direction. This looks like the direction where it has the greatest amount of spread or variance. It's not so much spread out in this direction, a little more tightly packed. So PCA is going to identify for us the direction of greatest spread or variance. To start, let's talk about what our data looks like. We're going to start with a collection of vectors in Rm. I'll think of these vectors as observations. Each vector consists of m different numbers which are measuring different variables. I'm going to take n of these vectors, so n separate observations. I can visualize everything by taking m equals 2. So for example, here I have a collection of about n equals 100 points in R2. This is my data. Before I can get started doing PCA, I have to shift my data so that it has mean 0. For example, this collection of points, shown in blue, has a mean shown by this red dot. If I take all these points and I shift them over so that the red dot is at the origin, I've shifted them to have mean 0. To accomplish this, I just compute the mean x bar by taking the average of the columns, and then I subtract that mean from every observation. Now I'll describe geometrically what it means to look for a direction of maximum variance. My data is now centered at the origin, so I'll draw a line through the origin, and I'll project all of my data orthogonally onto that line, so at right angles down onto the line. The result of that orthogonal projection is shown here with red circles. I now measure how spread out these red circles are. The measure of spread I use is variance. That's the sum of the squares of the distances from the origin. For this particular data set, I have a variance of 104. Now, let's change the line and see how the variance of the projected points changes. Here I've tilted the line a little bit clockwise. It's clear that the orthogonal projections of these points onto that line gives me a collection of red circles which is more spread out than the previous collection. And that's measured by a variance which is larger. I get 566 instead of 104. If I tilt the line some more, I see still greater spread of those red circles, a variance of 1,936. Tilting the line a little more, I find that I've maximized the spread of these projected points. I am at maximum variance. If I continue to tilt this line, I'll find my variance goes down. PCA will find this direction of maximum variance for us. I'd like to now create a mathematical formulation for this geometric problem of finding the direction of maximal variance. As before, let xj be a collection of n points in Rm. By a direction, I mean a vector q in Rm whose length is 1, norm q equals 1. I'd like you to recall that q transpose x is the dot product of q and x. It gives me the component of x in the q direction. This can be a positive or a negative number, but its magnitude is exactly the length of the vector that I get when I project x orthogonally onto the q direction. So if I start out with a data point x, and I project it orthogonally onto the q direction, I get a red circle. And the magnitude, the absolute value of q transpose x, is exactly the distance of that red circle from the origin. So if I have a direction q, and I want to measure the variance of all my data orthogonally projected onto that direction, I need to add up q transpose xj squared over all of my data points xj. As we've discussed, we'd like to maximize this variance over all choices of direction q. So mathematically speaking, we can state our problem as an argmax problem. In other words, I would like to find the argument q that gives me the maximum value of some q transpose xj squared, where q is restricted to have norm 1. The singular value decomposition will solve this problem for us. Before we take any SVDs, let's do a little setup work. I'd like to rewrite q transpose xj squared in a certain way. So first, let's write it as a product with itself. Then I'm going to observe that since this is a dot product, q transpose xj, I get the same thing if I take xj transpose q. So I'll reverse the order here. I'll take, instead of q transpose xj, I'll replace that with an xj transpose q. If I now reassociate this multiplication so that I'm associated in the inner part of this product, I have a funny way of rewriting Q transpose xj squared. It says Q transpose times xj xj transpose, which is a rank 1 matrix, times Q. Let's create a matrix X, which has as its columns my data vectors x1 through xn. Now, what is X times X transpose? Well, I've written them out here in terms of the columns of X and then the rows of X transpose. Matrix multiplication would give me x1 times x1 transpose plus x2 times x2 transpose plus xn times xn transpose. So in other words, X times X transpose is just the sum of xj xj transpose from j equals 1 to n. I should point out, just for curiosity's sake, that xj times xj transpose is an outer product, so it's a rank 1 matrix. So in other words, I've written X times X transpose as a sum of rank 1 matrices. I'd like to use these observations to transform the expression for the variance. So the variance is the sum of Q transpose xj squared. I can take this Q transpose xj squared and replace it with Q transpose xj xj transpose Q. So I've done that here. Now I can factor this Q out of the sum on both sides. So I have a Q transpose out here, then I have a sum of xj xj transpose on the inside, then I have a Q on the right. But as we've seen, this sum of xj xj transpose is just x x transpose. So I can write this variance as a very nice little matrix product. Q transpose x x transpose Q. Okay, excellent. We have rewritten our variance as a nice little matrix product in terms of the direction Q and the data matrix X. So the maximization problem we wanted to solve, which was to find the argmax of the variance over all arguments Q, becomes the argmax of Q transpose X X transpose Q over all arguments Q where Q has norm 1. I'd like to state and prove a theorem which tells us how to solve this maximization problem. First, start with the data matrix X. Take the singular value decomposition of X. Let U1 be the first left singular vector and sigma 1 the first singular value. Then the maximum of the variance is achieved at the argument Q equals U1, and that maximum is sigma 1 squared. In other words, U1 is the argmax of the variance, and sigma 1 squared is the max of the variance. Let's prove this theorem. The strategy for proof should be familiar. First, we're going to bound the quantity that we want to maximize. Then, we're going to achieve that bound with a particular choice of Q. First, let's discuss the bound. Take the singular value decomposition, U S V transpose of X. Then the term X X transpose in our expression for the variance becomes U S S transpose U transpose, where we've used the fact that V transpose V is equal to the identity. This expression for X X transpose is going to help us find an upper bound for the variance. So let's look at the maximum of the variance over all choices of Q with norm Q equals 1. Take that X X transpose and replace it with our expression that we got from the SVD, and this is what we have. Now, I can rewrite this term on the left, Q transpose U, as U transpose Q transpose. Now, looking at this expression right here, I've got a U transpose Q here and a U transpose Q here. So it looks a lot like the expression up here, except instead of Q, I've got U transpose Q, and instead of X, I have S. Now, U and U transpose are orthogonal matrices, so they are both invertible and length preserving. So as Q is ranging over all vectors with norm 1, so is U transpose Q. Therefore, if I want to maximize over all choices of Q with norm 1, a U transpose Q in here, I could instead just maximize over all choices of Q with norm 1, a Q in there. I would get the same result, since as Q ranges over all vectors of norm 1, so does U transpose Q. We've progressed from having to maximize this guy with an X X transpose in the middle to maximizing this guy with an S S transpose in the middle. Now S has a simpler form, it's a diagonal matrix, so you can bet that this is going to be an easier problem to solve. So let's look more carefully at Q transpose S S transpose Q. First, let's look carefully at S S transpose. S is an M by N matrix with diagonal entries sigma 1 through sigma p. S transpose is an n by m matrix with the same diagonal entries. Thus, S transpose is an m by m diagonal matrix, which has diagonal entries which are the products of the diagonals of S and S transpose, sigma 1 squared through sigma p squared. Here, as usual, p is the minimum of m and n to account for whether S is wide or tall. Now that we know what S transpose is, let's look at Q transpose S transpose Q. Write out Q and its components, Q1 through Qm. Then the product of Q with this diagonal matrix gives me the sum of the squares of the entries of Q, with coefficients equal to the diagonal entries of S transpose. Since sigma 1 is the largest singular value, if I replace sigma 2 squared with sigma 1 squared, I make this whole sum bigger. So let's do that with all of the singular values, all the way up to sigma p squared, replace it with sigma 1 squared. Then I have sigma 1 squareds as all of my coefficients, and I can factor them out and get a sigma 1 squared out in front, times the sum of Q1 through Qp all squared. I'm going to make this sum even bigger. We might be missing some terms of Q since we stop at Qp here, so let's add those on all the way up to Qm squared. Now I have all the terms in Q summed up squared. That's the norm squared of Q. So this is sigma 1 squared norm of Q squared. But norm of Q, by assumption, is 1. So this is just equal to sigma 1 squared. And our conclusion is that no matter how I choose Q, Q transpose S transpose Q must be less than or equal to sigma 1 squared. So remembering that this quantity is equal to Q transpose X transpose Q, this quantity, the variance, must be less than or equal to sigma 1 squared for every choice of Q. Therefore, the max over all choices of Q must also be less than or equal to sigma 1 squared. That's our bound. So now we'll show that we can achieve the bound with a careful choice of Q. You're probably not surprised that I'd like to take Q equals U1, the first left singular vector. Now I'd like to figure out what U1 transpose X transpose U1 is. But first, let's look at U1 transpose U. This product has a very special form. U1 transpose U is taking U1 and distributing it across all of these columns in a dot product. There's only one of these dot products that survives, and that is the dot product of U1 with itself. U1 dotted into U2, etc., all the way up to UN gives me zeros. So this result is going to be a 1 in the first entry and zeros in all the others. Very similarly, U transpose U1, that's just the transpose of the product we just took. Therefore, I'll get a column vector with a 1 in the first entry and zeros in the others. Let's come back to U1 transpose X transpose U1. As we showed earlier, we can use the SVD of X to rewrite this product in the following form. And we've done a little preparation to understand what these terms are. This whole term becomes a row vector with a 1 in the first entry and zeros elsewhere. And this becomes a column vector with a 1 in the first entry and zeros elsewhere. So we have the following product. This product just picks off the first element on the diagonal of S transpose, which is sigma 1 squared. Therefore, we have found a Q equals U1, which achieves the upper bound for Q transpose X transpose Q. Let's summarize. We found that Q transpose X transpose Q must be less than or equal to sigma 1 squared for any choice of Q with norm Q equals 1. Therefore, the max over all such Q's must also be less than or equal to sigma 1 squared. With a particular choice of Q equals U1, we achieve the bound of sigma 1 squared, since U1 transpose X transpose U1 is equal to sigma 1 squared. So, the actual maximum is equal to sigma 1 squared, and the argmax is the argument at which that maximum is achieved, and that's equal to U1. Let's come back down to earth here. We wanted to maximize this quantity because we wanted to maximize the variance in a particular direction. We found that the singular value decomposition solves this problem for us. It finds the direction of maximum variance. That's U1, the left singular vector of X. And it finds the variance in that direction, which is sigma 1 squared, where sigma 1 is the first singular value of X. The direction of U1 is called the first principal direction. The projection of our data X onto the U1 direction is called the first principal component. These are the red circles from our earlier plots. It also happens that these projections are given by U1 transpose X U1. We're ready to apply these ideas to an example. Let's look at nutrition data from the UK. In this table, we have 17 food categories for the 4 countries in the UK. Each entry in this table corresponds to the amount of that food category consumed in grams per person per week for the given country. What kind of variability is there in food consumption across the different countries? This is not a very large data set, but it can be hard to figure that out just by looking at it. We have 4 countries, or 4 samples, in 17-dimensional space. I certainly can't plot it in a straightforward way to visualize. I might be able to discern some numerical differences if I look carefully at the rows. For example, fresh potatoes. In the fresh potatoes row, I see 1,033 for Northern Ireland, which seems significantly larger than the other numbers for the other countries. Looking at the row for fresh fruit, I can see that Northern Ireland has a number which is now lower than that of the other countries. So it seems like I should be suspicious that Northern Ireland might be accounting for a large part of the variability across the countries. Let's use PCA to make this difference pop out. Let's look at the first principal component of this data. We put the data in a matrix with 17 rows and 4 columns, accounting for the foods and for the countries. As I said before, we can think of the data as 4 points in a 17-dimensional space. We're going to shift each of the columns by the mean so that the columns have mean 0 and the data is centered. We compute the SVD of the data matrix, and then find the projections of each of our 4 observations onto the principal direction U1. These projections are given by U1 transpose XJ U1. Unfortunately, each of these projections is a vector in 17-dimensional space. I can't visualize that. But they're all multiples of the same vector U1. So in order to visualize the projections, let's plot them all on a number line, just by plotting the coefficient of U1 that gives us the projection. I should point out that it happens that these coefficients are the same as the components of sigma 1 v1, where v1 is the first right singular vector. That's a straightforward consequence of the SVD, and I'll let you figure out why that's true. I've plotted these coefficients down here on a number line. You can think of this as the U1 direction in 17-dimensional space. The total variance along this principal direction is given by sigma 1 squared, which is about 315,000. The total variance in all of the data is about 467,000. So that one principal direction has accounted for about 67% of the variance. You can also see that, as we suspected, Northern Ireland is a clear outlier. So we should be looking at Northern Ireland to try to discern where a lot of the variance in food consumption across countries is coming from. So let's do that. Let's look down the Northern Ireland column and try to find numbers that are significantly different than the others in their row. The ones that pop out to me are alcoholic beverages, smaller than the others in the row; fresh fruit, smaller than the others in the row; and fresh potatoes, larger than the others in the row. This is good. We're starting to get a sense of where the variance in this data is coming from. But we're still inspecting it directly, which might be infeasible for a very large data set. I'd like to talk next about something called a load plot, which helps us identify which variables, or directions, are contributing the most to the variance. We've visualized the projection of our data onto the principal direction U1, but we have not visualized the principal direction itself. Visualization of the principal direction U1 is called a load plot. It's as simple as plotting the components of U1 on a number line, which I've done right here. I've labeled each of the components with the variable that it is measuring. A component of 0 in U1 would mean there's no variance in the principal direction for the variable corresponding to that component. Components of smaller magnitude mean that the variable is accounting for less of the variance in the principal direction. The variables with the largest components in U1 are fresh fruit, alcoholic drinks, and fresh potatoes. These are the variables that are contributing the most to the variance in food consumption across countries. So far, we've projected 17-dimensional data down to a single dimension to find a single direction of largest variance. But we can do more. We can find a second largest direction of variance, a third largest, etc., by doing something called deflation. We'll find that single direction of largest variance, and we'll deflate the data along that direction, and then repeat our process of finding a principal direction. As usual, let X be our data matrix with columns xj corresponding to our observations. To deflate this data, we remove the orthogonal projections of the data onto the first principal component. For example, if I take xj, I deflate xj by starting with xj and then subtracting off u1 times u1 transpose xj, the orthogonal projection of xj onto u1. I'll call this xj superscript 1, the deflated xj. The deflated data matrix will be written x superscript 1, and it has as its columns each of the deflated xj's. All of the variance in the first principal direction in our original data x has been removed from the deflated data. Therefore, if we find the first principal direction of the deflated data, we'll obtain the second largest direction of variance for the original data. We'll call this the second principal component. It turns out that the second principal component of x is actually given by the second left singular vector of x, which will be the same as the first left singular vector of the deflated data x. I'll now explain why the first left singular vector of x1, which is the second principal component of x, is the same as the second left singular vector of x. I'll do this by relating the SVD of x1 to the SVD of x. First, notice that in order to deflate each observation xj, we apply the same operator. That operator is a matrix I minus U1 transpose. Here I is the identity matrix, and U1 transpose is the rank 1 matrix that creates an orthogonal projection onto the first principal component. So, by the way that matrix multiplication works, I can deflate all my data to x1 by simply applying that matrix to the matrix x. Without motivating why I'm doing it right at this moment, I'm going to see what happens when I apply the deflation operator to the rank 1 matrix sigma j uj vj transpose. We have deflation operator applied to that rank 1 matrix. I can distribute the product across to the two terms. The identity times that rank 1 matrix will be the rank 1 matrix back again. And then this U1 transpose applied will be sigma j U1 transpose uj vj transpose. Let's notice this special product right here in the middle, U1 transpose times uj. The uj are orthonormal, so this product is either 0 or 1. If j is not equal to 1, then this product is 0. So this whole term drops off, and I'm left with sigma j uj vj transpose. If j is equal to 1, then this product is 1. So I'm left with sigma 1 u1 v1 transpose minus sigma 1 u1 v1 transpose, and it's equal to 0. So let's apply this observation about the deflation operator. First, let's start with x, and let's write x as a sum of rank 1 matrices as given by the singular value decomposition. So then the deflation of x will be the deflation operator applied to x, which is the deflation operator applied to this sum of rank 1 matrices. I can distribute the operator across the sum, and I get the sum of the deflation operator applied to each of the rank 1 matrices. But as we just observed, this product is equal to either 0 or sigma j uj vj transpose. It's 0 when j is equal to 1, and it's sigma j uj vj transpose when j is not equal to 1. So applying the deflation operator to the sum of rank 1 matrices just kills off the first term. It makes it a sum from j equals 2 to p instead of j equals 1 to p. We're now staring at the singular value decomposition of the deflated data matrix x1. The first singular value of x1 is sigma 2. The first left singular vector of x1 is u2, and the first right singular vector of x1 is v2. So we found that the second principal direction for x, which we define to be the first principal direction for the deflated data x1, is u2, and the variance in that direction is given by sigma 2 squared. We can continue to deflate to obtain third, fourth, etc. principal directions. But for now, let's go back to our example and see what we can learn from the second principal component. I've plotted our 4 observations orthogonally projected onto the plane spanned by the first and second principal directions, u1 and u2. We've already seen the left to right spread along the first principal component that made Northern Ireland pop out as being different from the other countries. Now we've got another direction of spread, up to down, along the second principal component. This is making other differences pop out. For example, there's a pretty big difference between Wales and Scotland along the second principal direction. To see what's causing this, let's look at a two-dimensional load plot. To create the two-dimensional load plot, we'll plot each variable using the components of u1 and u2 for its coordinates. Looking left to right, I see something I've already seen. The variables that have large components in the first principal direction, such as fresh fruit, alcoholic drinks, and fresh potatoes. Now, looking up and down, I see variables that have large components in the second principal direction. These are fresh potatoes and soft drinks. This is where I should look to try to find and explain the variance between Scotland and Wales.